to have Markus Greiner visiting us from Harvard University. Markus has truly pioneered the field of quantum simulations with ultra-cold atoms. This is a field that had its birth really in an experiment that he did as a PhD student in the group of Ed Hench in Munich, where he loaded a Bose-Einstein condensate into an optical lattice and watched it undergo a phase transition from a superfluid to a strongly correlated non-insulating state. As a postdoc at GILA with Debbie Jin, he switched his attention from bosons to fermions and formed the first fermionic condensate. Since 2005, he's been a professor at Harvard, and in his group at Harvard, he invented the quantum gas microscope, a very powerful tool for probing and manipulating the quantum Manybody system at the single particle level. He's used this to do beautiful experiments really measuring entanglement in the quantum system, and through that lens, gaining insight into how a closed quantum system thermalizes. And most recently, he's turned to probing lattice models of fermions that are highly relevant to understanding the connections to electrons and condense matter. And I think he will show you some very beautiful pictures today in that context. So I will let him do the talking soon, but just to mention, he's of course received numerous awards for contributions both to condensed matter and atomic physics. Just to mention a couple, he's received the I.I. Rabi Prize of the American Physical Society. He's also been recognized with the MacArthur Genius Award. And so we're looking forward to hearing from you today.
Yeah, thank you very much, Monica, for the nice introduction. Yeah, hello everyone. So it is my great pleasure to tell you a bit about kind of the marvels, how we can use ultra-cold atoms to build artificial quantum systems that are really highly controlled, where we can really see everything that's happening, but also control everything that's happening. Really build models, program, model Hamiltonians essentially. And so I think there's a lot more to come actually. And I would, like in the second part of my talk, I will show you what we do with the fermionic atoms. And part of it will also just be telling you a little bit about what I think, or the kind of things that we are now starting to do. I will also tell you a little bit about, in between, about Manybody localization. I will keep that a little bit short to have time for the fermions, and it kind of takes a bit, wants to dive a bit deeper into that, or that could fill an entire talk, I guess. So, but I at least want to give you a little bit of the flavor for that. Yeah, so we use ultra-cold atoms. We always start with laser cooling. Here's just a movie I took, I guess a long time ago, where you see atoms that are laser cooled. Laser light slows them down, and you see they fly apart pretty slowly. They have fluorescent light here, so that's why you can see them. They fly apart much slower than atoms at room temperature in a gas, which would fly with the speed of sound, right? And so these are at the microkelvin regime. It's of course only the first cooling step. Ultimately, the temperatures that we have are in the nanokelvin regime. So I have a logarithmic temperature scale here. If this is room temperature here, if you work with liquid helium, you're slightly below room temperature, and on this scale at least. And with the ultra-cold atoms, we're typically in the nano or even picokelvin regime, which surprisingly is about as cold as the LHC is hot. Like if you go 13 orders of magnitude down in temperature, that's where we are. If you go up, then you are at a few tera electron volt, where the high energies, like where the limit of the energies is for accelerator experiments right now. Yeah, but why do we want to get cold, right? You would think everything is at standstill. Why study cold of gas of atoms that's that cold? Of course, what happens is that quantum mechanics really takes over. And my gas starts to behave completely quantum mechanical. Atoms are delocalized as I will show you, and can be, so to say, at many places at once. And we can form a quantum gas, really, to study models, to study really many-body quantum models, because we can also have the atoms interact with one another, which gives rise to very interesting many-body quantum mechanics. And one main application of this idea is the idea, kind of following ideas by Feynman, essentially, that we can build a quantum simulator. That we can, like if you have a many-body quantum system that's too complex to understand, we can build a model which is much more controllable, much more accessible, and then we can study this model system in order to try to learn about nature. And so what we are essentially doing is we build a model system for how electrons behave in quantum materials. Like, as you know, inside every piece of material, the valence electrons essentially form a degenerate quantum gas. And if this becomes strongly correlated, this gives rise to really interesting phenomena that are often not really understood, because it is really hard to compute, to calculate many-body quantum mechanics, effects like high-temperature superconductivity, topological materials, and so on. And so here, we can build a model system where a quantum gas of atoms moves in an optical lattice, which is a periodic potential landscape formed by light, essentially. And so this simulates, so the atoms moving in the lattice simulate how the electrons move in a crystal. What we really wanted to also add to this mix is the ability to control the quantum system on a single latticite level. And so for that, we developed quantum gas microscopy. Here you see a sketch of kind of a two-dimensional quantum gas, which is in the focus of a high numerical aperture objective here. And so we can have many atoms in the focus of an objective, and amazingly, we can actually image all the individual atoms. Here's a picture of the core of the experiment. Our atoms at these nanokelvin or picokelvin temperatures live only a few micron below this room temperature surface here. It's a super polished surface on the bottom, where we can trap the atoms and apply all kind of light potentials to form optical lattices and other arbitrary potential landscapes. And then here is a lens which is part of the high numerical aperture microscope lens that is on top. The real experiments are a bit more complex, of course. You need lots of lasers that are fed over by these fibers to the actual experiment tables. But so these machines are pretty complex, maybe the most complex atomic physics experiments that still fit into a lab. But as I said, they still fit into a lab, so it's actually that is very nice. You can still work with a few graduate students on it. And when I built these originally as a graduate student, it was a lot of fun to do that, because you learn about all kind of technologies. You have to push all kind of technologies to the limit. So that's part of the fun if you work in this field. Yeah, and then if this all works, what we can do is we can take pictures like this, where the atoms in the optical lattice, if we make the lattice very deep, then the atoms don't move anymore. And we can shine light onto the atoms. We do it specifically in a way to laser cool them in that lattice, and that scatters photons. And those photons we can image with this high resolution microscope objective, and then we get pictures like this. So each of the dots here is exactly one atom on the lattice side. And if you zoom in, you can see that all the atoms are actually arranged on a perfect grid. So that's our optical lattice. We take a snapshot. Typically, we measure the parity here. If two atoms form a molecule and it appears dark, 3 appears 1, and so on. But if you think about it, what's really special is it's taken this perfect snapshot. Like, this is as if in condensed matter you could stop the time evolution, like stop time, and measure the position of every single electron and the spin also. That's the kind of thing we can do, of course, in condensed matter physics. People wouldn't know how to do something like this. And I think, as I will show you later in the talk, this could add really qualitatively new possibilities to study this many-body quantum mechanics. So how do the... sorry, this is actually the wrong slide. Yeah. How do the atoms move in an optical lattice? So here we've done an experiment where we prepared exactly one atom in the lowest band of exactly these lattice sites here, and the atoms coherently tunnel through the lattice, right? So if we start the time evolution, sorry again, if you start the time evolution here, you see that the atom wave function would spread out fully coherently in the lattice. And in the experiment, we can do that. What I show here is, after some time evolution, we take a snapshot and we find the atom in some position. Of course, if the atom delocalizes if the atom moves in the lattice, it really delocalizes at a wave. It's in a superposition of being here and here. And if we image it, we collapse this wave function. The first scattering photons kind of entangle the position of the atom to the photonic field, and then we find it at a particular position. But if you repeat this measurement over and over, then you can see, you can essentially measure this wave function, and we see then that it does, as a function of time, does this ballistic quantum walk. The contrast of the projector is a bit hard to see, but you can really see this fully coherent motion of the atoms, right? It looks exactly what you would expect for a free particle, and it looks very different for what atoms or what particles would classically do. If you had classical particles in here, you could imagine them doing like a quantum walk or so, where you would get a diffusive process. So instead, these atoms move coherently. How coherent? This is actually nice to see. We can look at real space Bloch oscillations. If I put an atom on the side and I tilt the lattice, what would you expect to happen? Well, classically, you would expect this to roll downhill, right? Quantum mechanically, if you have such a localized lattice and you do a Bloch oscillation, well, the localized state is a superposition of all the Bloch states. And so what would actually happen is the wave would spread out. So now you're in a coherent superposition left and right? But if you keep going, it should come back. And it does perfectly. And so the fact that this comes perfectly back to its original side really tells you the degree of coherence. Like when the atom is delocalized over 10 sides left and right, this is completely coherent. So this is how individual atoms move in the lattice. Now, of course, we can use many atoms. And these atoms interact very cleanly with one another. All that happens is if you have multiple atoms on the same side, that just raises the energy a little bit. But you can imagine how this becomes quickly very complicated. Every atom is everywhere, essentially, but also sees all the other atoms, which are likewise everywhere. And if you have strong interaction, if the interaction is on order of the tunneling, you can imagine that this can give rise to complex quantum states, and that something like this is actually hard to track on classical computers. Right. So, the first experiments we did already a while ago with, as Monica said, without a microscope, superfluid Mott transition. Right? If you have bosonic particles and if they are weakly interacting, then every particle is delocalized over the entire lattice. Right? So on a single side, you have a coherent superposition of having no particle, one particle, two particle. But if you then adiabatically increase the interaction, then you can do a quantum phase transition to a Mott insulator where you have exactly one particle per side, as you see here. So we have used the microscope to study these kind of transitions, for example, and to study a lot of physics that occurs here. You can play additional tricks. You can give the atoms spin degrees of freedom, also look at magnetism, all kind of things like that. I just want to briefly show you one experiment that we did recently on quantum thermalization, on non-equilibrium physics in such a system. The basic idea here is, imagine a closed quantum system here. So here I have a chain of 6 lattice sites starting with a mod that are prepared with a mod insulator, exactly 6 atoms on 6 sides. What would happen if all of a sudden we quench the system away from the ground state? So we prepared the ground state, the mod insulator, and then we hit it with a hammer, like we quench the Hamiltonian to where the ground state would be very different. And then we will get a very complicated time evolution. And like we project the ground state into a new set of eigenstates in the new Hamiltonian, essentially. What would happen in such a quench? Well, interestingly, first of all, if you start with the pure state here, while the dynamics is very complicated here, kind of chaotic, it will actually remain in a pure state. How could I show that a Manybody state is still in a pure state? The amazing thing is that in the microscope we can develop, we have developed a way, a degree of control that we can do Manybody interference. We can create 2 identical copies of such a Manybody quantum system, and then we can put them onto a beam splitter, like we let neighboring lattice sites interfere. And this is exactly like homomundal interference of photons, except here it's atoms. So we have 2 Manybody systems of atoms, and we let them interfere on a beam splitter. It turns out, if we do that, we can directly measure the quantum state overlap between these 2 quantum states. After this beam splitter, if you look at the parity, it tells us trace of rho 1, rho 2. And that's really special. If you think about both of these states, we have done these experiments where the state lives in a 20,000 dimensional Hilbert space. So I can quantum compare 2 Manybody quantum states that live in a 20,000 dimensional Hilbert space. Right? How else would you do that? If you have a state, I have a state, and we ask are they the same or not, it would be very hard. You would have to do tomography or so, which is not even known how to do that. Here we can just interfere them, and a parity signal tells us the quantum state overlap of the 2. And so we have implemented this, and if they're the same, so one application of this is that we just measure the purity of the Manybody quantum state, like trace of rho square. And we can show that, yes, even as the time evolves here, these 2 Manybody states remain indistinguishable. They remain a pure state. They remain in a pure state. And what's interesting here is here I can show under this unitary dynamics, the state remains a pure state. That means there is no entropy occurring. Right? It's a non-entropic state. On the other hand, if I measure any local observable, I will find that after a fairly short time, this will be completely indistinguishable from a thermal ensemble. If I, for example, measure the atom number distribution here, this looks just like your favorite statistical mechanics ensemble. And you can pretty much measure what you want. A small subsystem, if you measure on part of the system, it's indistinguishable from thermal. So how can this be? How can, on one hand, how can this look thermal, which you would associate with maximized entropy, and at the same time you have shown that there's no entropy at all? The solution to this is that this entropy here that you find is entanglement entropy. Okay? So all of the entropy only occurs because you're only looking at part of the system, and your kind of ignorance, like the fact that you don't know about the rest of the system if you only look at 1 or 2 sides. So this one side is highly entangled with the rest, and if you trace over this, then you get something entropic here. This is following the idea of eigenstate thermalization. So here, statistical mechanics really emerges from coherent Schrödinger dynamics, and that was really fascinating to me when I this, that you can really have a situation where coherent Schrödinger dynamics, where statistical mechanics naturally arises from that. And I can see how part of the system looks completely thermal, even though I have shown that the many-body quantum state is a pure quantum state with no entropy at all. I don't have time to talk about it. We then actually went on to measure the entanglement entropy directly. We can do this with the same homomandal interference, and then you can see that for a small system, the entanglement entropy looks exactly the same as what you would expect for the thermal entropy. But as you then go to the whole system, the entropy comes down again, and if you look at the entire system, there is no entropy at all. So this makes perfect sense that entanglement gives rise to this. Or you can also think about it that a subsystem is really in a coherent superposition of all the different possibilities of your statistical ensemble, essentially. And this is described, this quantum thermalization is described by Eigenstate thermalization hypothesis, where you say that all this behavior can already be understood by looking at one eigenstate of the system. And so it's a really interesting direction where the statistical mechanics naturally emerges. I don't have time to talk about this in detail. What I do want to briefly tell you about is a famous example where eigenstate thermalization breaks down. And this is in many-body localization. So this eigenstate thermalization, this always occurs for all known situations except if it's an integrable system or except if you have a many-body localized state. So what is that? What has been proposed is that if you have a disordered system, then you can have a situation where it doesn't thermalize, where it kind of gets stuck and does not thermalize. This is related to Anderson localization, but in an interacting system. And so to be able to do this experimentally here, if we again start with the initial mud-insulator state and then we quench it, but in addition we now add a disordered potential, and then in the end we count the atom number on every side. From that information, we were able to explore this many-body localization. The idea is that the particle degrees of freedom, they localize, and we are able to show that by measuring the G2 correlation function. Like if you find a particle on one side, what's the probability to find another one close by? If in a thermalizing system, after a fairly short time, that probability is equal anywhere in the system. So all the particles, they really spread out, they move. But in the many-body localized system, I can see that they are localized, the particles, they don't get very far. So particles are localized, as I've indicated here by these little mountains. And we have measured the localization length here as a function of disorder strength, for example. Well, so far so good, but MBL is more than that. MBL, so this behavior you would already get for non-interacting Anderson localized state. The difference in many-body localization, this is famous for, on top of this, you have a slow logarithmic growth of entanglement entropy. Essentially, these localized orbits here, they still weakly talk to one another, which I've indicated by the arrows here. They talk to each other over long distances, really in a very suppressed way over these exponential tails. They weakly talk to each other, and that gives rise to a very slow, thermalization, or to a logarithmically slow growth in entanglement entropy. Experimentally, this hadn't been seen. If you calculate this, if you calculate the entanglement entropy versus time here, you see that normally it always goes up to here. This blue one is an Anderson localized state. If you then have many-body localization with interaction, you have a very slow logarithmic growth of entanglement entropy here. But what we found is that you can separate these two. This is really the localization of particles, whereas this one here, this is really the entanglement entropy of configurations, you could call it, kind of like the rest from the particle part. I can't, I'm sorry, I don't really have the time to give you the complete story here today, but the important part is we can measure a correlator here, which is a fantastic measure. We found numerically that this is really proportional to the entanglement entropy, to exactly what makes a difference, like what really characterizes this Manybody localization. You can see this logarithmic growth here, and this we can do by measuring a correlator between different configurations. If you look just how different, like if you let the system evolve for a time, how different patterns are being correlated in different parts of the system, we can measure the slow logarithmic growth of entanglement in the system here. And you can really separate these two effects. The first part is the same as an Anderson localization. This had been seen before. We have localization, but after about 10 tunneling times, nothing changes anymore. But then this part sets in, and you have this slow logarithmic growth of entanglement entropy. And in other words, this follows area law here, this particle localization, whereas this here is is a volume law that slowly increases and gives rise to the logarithmic growth of entropy. So what we're excited about is that this is really the first time that you can see this logarithmic growth of entanglement, and so it was really fascinating to learn about these systems. Good. So this is all what I wanted to say about the measurement of non-equilibrium systems here. We can directly measure entanglement entropy, which we have started using to study different quantum many-body states in equilibrium and out of equilibrium, like the quantum thermalization. And I think this will be a very useful tool in the future for all kind of experiments. I would like to switch gears now. So far, I have been telling you about our experiments with bosonic atoms. Let's start about fermionic atoms. It's of course very nice to work with fermionic particles, because that's much closer related to how electrons move in a material, for example. There you have these fermionic degrees of freedoms, and that give rise to the interesting physics. I would like to really pay tribute to David Jin for this, who really pioneered these ideas of working with ultracold fermionic atoms. She unfortunately passed away a year ago, and but like I really loved her pictures always. She would show that the fermions are really a bit more independently minded particles. Right. So what we are doing is to have these fermionic atoms in an optical lattice. These are the students and postdocs involved in the experiment. And so the idea is that we pretty much build a perfect realization of a very simple Hamiltonian. Namely, the most simple Hamiltonian you could think of that produces strongly correlated physics with fermions on a lattice. It's simple in the sense that, well, you just have fermions in two spin states. They can tunnel between neighboring lattice sites, just like what I showed you earlier. And two atoms on the same site, they repel. Well, they're fermions, so you can only have one atom per spin state on the same lattice site, because we only have one orbital, like only one band, or we are using only one band. Yeah. And so this is the Hamiltonian. It's deceivingly simple, because as the condensed matter physicists among you know, while it looks really simple, it's actually not really known what physics it gives rise to. Right? What is certainly known is that at unity filling, it gives rise to an anti-ferromagnetic state, which is very close to a Heisenberg anti-ferromagnet. But it becomes really interesting and hard to understand once you go away from half filling. Like if you have holes, if you have doublons in there, in the strongly correlated regime. Interestingly, it is believed to be a minimal model maybe for high temperature superconductivity, or for materials like this. The phase diagram, while not really known in detail, is believed to resemble or to be similar to what you have in unconventional superconductivity. There's probably like a pseudo gap here, strange metal behavior, and so on. But it's really hard, like even the model is so simple, it's really hard to compute it. Like in quantum Monte Carlo, you can maybe do 8 by 8 or so, not extremely low temperatures, or for if you want to study non-equilibrium, typically you can calculate 4 by 4 sites on your laptop and 4 by 5 sites if you have a supercomputer. Kind of, it scales so unfavorably because it exponentially scales. The nice thing is that with cold atoms, you can really build a pretty much perfect realization of this model. This was originally proposed by these gentlemen, that and there has been a lot of work over the years in this direction. Of course, the challenge is to get to colder and colder temperatures here. Right? What we really wanted to do is build an experiment where we combine such a system with a quantum gas microscope, where we can see the individual atoms. So we built this quantum gas microscope and get pictures like this. So each of the dots is again one atom, one of the lithium atoms. This picture I just showed you is still at high temperatures. At high temperatures, you have a metallic state here, right? But if you then lower the temperature, if the temperature is smaller than the interaction energy, then you get a Mott insulator if you're at half filling, as you can see here. So there's one atom in every lattice site, which again here we could nicely show in the microscope directly. But then if you get to even lower temperatures, it becomes more interesting because there is some exchange energy, I will come to this, which gives rise to magnetic interaction between the particles. And so this is where we want to get into the anti-ferromagnetic state and so on. There have been exciting experiments already by Tilman Esslinger and by Randy Hewlett. They had temperatures which were a bit above the transition to the anti-ferromagnetic state here, but they could see the onset already of anti-ferromagnetic order. Okay. At half filling, this model actually is equivalent to like a Heisenberg model. You have you can think of this as a spin model. Why is that? Why would fermions in this model like to form an anti-ferromagnet? As you saw in the Hubbard model, there's no explicit spin-spin interaction between nearest neighbors, right? You only have the on-site repulsion, giving rise to the Mott insulator and the tunneling. Well, but this is it's fairly easy to understand. If you have a Mott insulator, then if two atoms or neighboring sites are in opposite spin states, they can still virtually tunnel to the neighboring site. They can delocalize slightly, which is always energetically favorable. They could even exchange, right? But if they're in the same spin state, then even these virtual excitations are forbidden by Pauli exclusion, right? And so it's energetically favorable to have opposite spins on neighboring sites. Okay, yeah, and the onset of this has already been seen here. Okay, so but what we really wanted is get to colder temperatures and get right, and make a real anti-ferromagnet. So how would this be possible? Well, the nice thing is that in the microscope we can play additional tricks what people couldn't do before. We can really form arbitrary potential landscapes. Like we build projectors, like laser projectors, where we have spatial light modulator like you find in a video projector, but illuminate this with a laser and then project pictures of that onto the atoms to create potential landscapes, for example. And so we have additional tools, and with that we can now build additional complexity, and for example make a coupled system. I don't quite see the lines here. A coupled system between two different regimes. If I have two systems that I bring into thermal contact, and if the level spacing here is different, like if the specific heat is different, then you could imagine that the entropy would move from one part of the system to another. And that's exactly what we do. The system we want to study here is where we want to create the anti-ferromagnet as a mod insulator, but we could bring this into thermal contact with a system that acts as a reservoir. In this case, if you have a dilute metal, then excitations cost much less energy. So if this is in thermal contact, excitations would actually move over here into the metallic phase. We realized this by engineering a potential landscape with the spatial light modulator that I was mentioning. So with this, we can really program a potential on top of the optical lattice on a single side level. Here you can see you can even write these letters. But if you use it to make a potential of this shape, then we can make a mod insulator here and a dilute metal in the wings. If we take a picture of this, it looks like this. Here's a mod insulator here, and all around is this halo of the dilute metal. If you do that, what happens to the mod insulator here? Let's have a look and let's image one spin state only. We can remove the atoms of one spin state by shining resonant light and can only focus on one spin state. And if you do that, we get pictures like this. So here you see a picture of, here's a raw image, and if we fit it, it looks like this. It looks a lot like a checkerboard. We're only imaging the up atoms, and this is a mod insulator where like pretty much every side has one atom. So that means all the white spots here, they are actually places where we would have a spin down atom. And so you can see kind of a nice checkerboard appearing. So we have gone into the anti-ferromagnetic state here.
Can I? Mm-hmm. I haven't read this paper. Mm-hmm. But what determines which direction is up and which direction is down?
Excellent. Yes. So this is in fact on my next slide, because this is, you could call it a lucky shot. Here the direction of the Néel order happened to point into the direction in which we measured. So what do you mean the spin direction, right? Exactly, because this is a Heisenberg magnet. And it's SU2 symmetric, so we really have how I think about it, or how you can think about it, is that the Néel order in each shot will point into a different direction, right? And we are always measuring. Let's call our measurement axis the SZ direction, right? If the Néel order looks in the perpendicular, points in the perpendicular direction, then we don't see long-range Néel order. If it happens to point in the Z direction, then we see the Néel order, right? And so, in fact, we can record the full counting statistics here, right? So we just keep taking pictures and look at the statistics, right? Yeah. So we can measure the correlator, so average over all kind of pictures and all kind of orientations of the Néel order. We can measure the amount of anti-ferromagnetic correlation. This is plotted here. And so what you see is that we have anti-ferromagnetic correlation across the entire sample that we have. Also, if we plot how it depends on distance, well, what do we expect? So this should be kind of described by a nonlinear sigma model for long distances. And in 2D, the correlation should always decay exponentially. It's kind of a little bit similar actually to BEC physics here. Like our order parameter lives on a sphere here. This is our spin, right? And so the staggered order goes like this. This is kind of reminiscent of BEC, where the order parameter lives on a ring, right? But since it lives on a sphere, it's a bit more fluffy, hence it decays a little bit faster. if you have SU2 symmetry. And so then instead of BKT physics, you get exponential decay in 2D. And that's in fact what we see for any distance. This tail fits very nicely to an exponential. Okay. But also that is not the full story. What you can also see is that at short distances, we have much more anti-correlations. And this also makes sense. If you actually, if you think about it, the classical Néel state is not the lowest energy state of a Heisenberg magnet, right? What you really have is you have a competing process. Well, let's think about what would happen on a double well. On a double well with one spin up and one spin down fermion, you would get a singlet state, right? Which means that independent of the basis you measure, they're always opposite. They're opposite in X, Y, or Z, right? And so in Heisenberg model, that gives you 3 times the energy gain compared to a Néel state. So a perfect singlet state you can only have on a double well. For long distances, the best you can do is a Néel state where you have this checkerboard pattern, but that can only work in one spin direction, as you saw. If you look in the opposite, then you can't be anti-aligned. So what the system chooses is a compromise of the two. For short distances, it has the nature of a singlet state, and independent of the axis you choose, you always find strong correlation for short distances. And for long distances, you have this classical Néel order, essentially. Yeah. The correlation lengths you can see here, and how it diverges below the and so we can see that this is very nicely described with the nonlinear sigma model, where the correlation length depends on the temperature like this. Yeah, so you can see, so we have reached, we're really excited that we reached kind of like the first low temperature phase of the Hubbard model, this anti-ferromagnet. But of course, what we really want to do now is to get into these regimes that are hard to understand. I mean, there's no, for the Heisenberg model, there's no new physics, right? This is understood all the way down to very cold temperatures. Where it becomes interesting is if you now add holes to the system. If you dope the system, if you have essentially charge that can move around and interact with the spin degrees of freedom. That's when it really becomes interesting. And so next I would like to tell you, to give you a bit of the flavor, what happens there.
Actually, before you can I ask a related question? These optical methods are doing great violence at one moment.
Like we stop time, actually. Like we stop the time evolution, we turn off all the tunneling, and then we just do a kind of an instantaneous measurement.
Now I understand. So that means there isn't any easy way to tell if this thing conducts atoms. It's a conductor.
Not if you just take a snapshot, right? But then we can do other things to test those kind of things. Right? Like we could measure transport. We could measure, what I will be showing you is kind of some coherent motion of holes, for example. We could measure all kind of things like that.
Well, and I'll be quiet because I want to hear. But in order to do this experiment, you have to make the chemical potential non-uniform.
Yeah, we can do that, right? With our video projector for laser light, we can create arbitrary potential landscapes, and we can even change them in time and create flow, and so it's very programmable, essentially. And there have been, not in the Fermi Hubbard model, but in the bulk model, there have been nice measurements on transport and wires. But like, for example, one thing I would be excited about is building a Josephson junction here, right? And then looking at...
One thing at a time.
Yeah. So, right. I mean, that could be ultimately one way to, for example, test if one has a superfluid autoparameter or something, if one wanted to. But yes, one thing at a time. Thank you. Good. So let's look at, I would like to discuss a little bit about how these holes move in this anti-ferromagnetic background to give you a flavor for the richness of this of the physics that happens here, and also our ability to look at that experimentally. The first experiment we started doing, so all of the things I will be telling now are very preliminary kind of, this is all work in progress. None of that is published. Imagine, so what we did here is we kind of made a state where we kept one row of lattice sites empty, and then we only turn on the tunneling horizontally. So you have kind of an anti-ferromagnet here, or in this particular case, this was a bit higher temperature, but you have an array of 1D systems where you start with a localized hole. And we can do this by just raising the potential on one lattice site, and so that keeps the site empty, so we have a localized hole. But now we can turn off that potential, and so the hole suddenly becomes movable. Like it can move around, and it can move just like the experiment I showed you earlier, where we start with the one atom and look at the quantum motion of that atom. Here we can look at the quantum motion of the hole. And so then we let it move, and then we take a new picture and record where we find the atom, and take statistics of where it moved. And if you do that, we find, it's just a quantum walk again. So this is in 1D, we find that the motion of the hole is perfectly described by a quantum walk, just the motion of a free particle, essentially. Why is that? Well, it's actually quite amazing. Despite the complexity here of the spin system, in a 1D system here, you expect perfect spin-charge separation. Essentially, the hole can just freely move here. It doesn't care about the spins, because in a way the spins don't care about the holes. There have been experiments by Emanuel Bloch and Christian Groß in Munich where they look at the spin sector. So we look at the charge sector here and see that the hole moves freely. If you look at the spin sector, then you can also see that the magnet doesn't care about the hole. If you go and you have perfect spin-charge separation. What is special here is that it's very easy for us to see that directly. First of all, with the motion of the holes, but also in the spin sector. If you would look in momentum space and sprinkle in holes, your anti-ferromagnetic peak would broaden a lot, because each time you have a hole, the magnet is kind of spaced by one side, essentially, and gets out of sync. Okay? But if you go into squeeze space, where you take out all the holes and shove the magnet together, right, which you can do in data analysis here, then you actually find that you get exactly the same property as in a magnet where you don't have any holes. And so this can directly show this spin-charge separation. And the reason why I pointed out is in condensed matter physics, this would be called hidden order, because you can't see it, right? Because if you look in momentum space, you would only see broad peaks, where in reality, if you took out all the holes and shoved the magnet together, you would actually see the physics. And in the paper by Emanuel, you would see the same physics as in a magnet without holes. And in the paper by Emanuel Bloch, you see that all the curves lie exactly on top of each other if they do this process and go into squeeze space.
Excuse me.
Yeah.
I'm a bit confused. Why is it a one-dimensional problem? The image is
The image is two-dimensional. We turn off the vertical tunneling. Like it looks 2D here, but every horizontal row is independent because the tunneling in the y direction is 0. No? Okay, so here it's simple, spin-charge separation. And one other thing is we can also use a pair of holes, and then we can actually show this is hole number 1, hole number 2, how they're anti-correlated. So this is exactly what you would calculate for two either hardcore bosons or two fermions. So you can see they really behave as very nice quantum particles here in this 1D system. Let's now go to 2D. And the exciting thing is that the situation completely changes here, right? If you now have a hole and it moves, it also shoves the the atoms over. And a simplified picture of this would be kind of this idea, like if you start with a classical nil state and the hole moves here and then moves here, kind of a simplified picture would be that you can kind of tell where the hole went by looking at this, by the string. So this was proposed a long time ago. And so this is the kind of thing that would happen here. It's a bit hard to see. If you do this experimentally, if you let the hole go, we see that for very short times it looks like a quantum walk, and then immediately it looks more like a diffusion and stays together. But this is we have to take more data on this. What we can now really do is we can really look at this in real space, and we can test different models and ideas. And one of the ideas that we could test is, does it maybe behave the following way? Does it maybe behave in a way that if the hole moves to here, it leaves behind this string, and maybe the string is a fairly stable object. Maybe the string is kind of like a binding between a spinon that is here and a hole on here. The spinon now would move more slowly with the super exchange J. The hole can move quickly and be delocalized around that spinon with T. It's kind of like a dog on a it's a bit like a hyperactive dog on a leash around the spinon, and they somehow move together. Right? The nice thing is we could directly test these kind of things, right? We can inject a hole, and now we started to just look, do we find these kind of strings, and what happens over time as a function of time? And maybe, right, what happens, what holes maybe bind, like what happens if we now adiabatically inject two holes? Would they bind somehow? Maybe if two spinons annihilate, there would be hole-on string, hole-on object. Or maybe it's different. Maybe they both still form a string, spinon, hole-on object, and somehow they attract. And so on. What I find interesting is that for us, this should be, I think we are kind of at the brink of the temperature where this should become visible. We actually looked at some equilibrium data where we find like via data analysis in the spin sector, we look for these strings. We find that it's about like the number of strings we identify is about 3 times the number of strings that you would get if you just randomly add holes that do not have strings. So we have some evidence emerging that there may be something like that. But then we really want to inject this adiabatically and look for these object and look for this physics in real time emerge essentially. And for example, if we could do things like inject 2 holes and see, do they just move the same way as a single hole would move? Or is there some correlation between their motion? Do they maybe even form some kind of bound pairs? Maybe even something like a Cooper pair or preformed pair or so. And what is how is the position of the hole now entangled with the spin sector? Do I find these kind of strings? How do they arrange with respect to each other for multiple holes? I think what's exciting here is that all of this physics is very much in real space. And you could not access this neither in experiments, as far as I know, so far in condensed matter, where you couldn't take a snapshot. You can only, you can measure maybe SDM locally, but these are time averaged measurements. You couldn't just take a snapshot and look for this. And also, in terms of correlation function, you really want to get a complete snapshot. If you just ask for, this is not described or not characterized by 2-body correlation function, 3-body correlation function. It's a much more complex kind of thing. But here we should be able to directly watch that and look at that. And so we're really excited to start these kind of experiments. Of course, then once we started kind of like microscopically, we can look what kind of phases emerge. We started to look at that. We haven't found anything striking yet, but also you could see how this, of course, changes as you add additional terms to the Hamiltonian and so on. And so these are the kind of things that we started to do recently. Yeah, and so the exciting thing is that, as far as I understand, kind of there's no theory right now that can really test, or no numerics that can test these kind of fairly simple ideas to what extent they are true. You can do certain things, but you cannot simulate things like this on a computer. And so this is really exciting to me that we essentially have a quantum machine that can do this quantum simulation in a regime where you cannot compute things anymore. Yeah, so with that, I would really like to, let me get you a brief outlook. Of course, we also want to get colder. And I think, the experiments are really at a state now, like in condensed matter physics, when you just had liquid helium. Like we just start, like our starting point is like 4 Kelvin, right? And now we got a little bit colder. But now we have lots of ideas how we can play the toolbox to get significantly colder. For example, we could, so this game with a 2-coupled system worked beautifully, except if you just have a metal and a mud insulator, we get at most a factor of 3, and that's exactly what we got. What if you, for example, make a double layer system? What if you also make the tunneling different in 2 coupled layers, and then we can decouple them, we can suck all the entropy in 1 layer. So we believe that this should be possible to get much colder, for example. So it's really like starting with 4 Kelvin and now kind of doing all the kind of advanced cooling tricks. One other trick that we do is this idea you could also do perfectly by starting with a gap state here. And so we tried this in the experiment. A nice gap state would be if you make a band insulator. So we tried to make a band insulator in the center with the metallic halo. And what we found is that we get perfect band insulators. We can really completely, so sorry, the picture, this is white here. If there are 2 particles per side, it's also showing up as white. And sorry, the projected cuts off the lighter colors. But what you see here is that you get a perfect band insulator, or very near to perfect band insulator. The entropy per particle is about 0.018 keV. So that is significantly lower than the kind of entropy you would need for D-wave superconducting state or something like that in terms of temperature. It's much lower than what we have so far in our anti-ferromagnet. Of course, the challenge now is to turn this relatively boring state of a band insulator into something interesting, like the mud insulator with the magnetic. But there are many different ways. We actually we tried the brute force approach of just increasing the volume. That didn't work particularly well, not surprisingly, because you need a lot of particle flow in this insulating regime, which you wouldn't expect to be particularly fast, and you cross the entire phase diagram from infinitely doped from both sides. But we already found pretty good anti-ferromagnetic correlations there. But if you do a bit more sophisticated things, apply staggered fields or turn one lattice site into a singlet, for example, then we should be able to really create very low entropy states here. And if you choose a good pathway, for example, maintaining a charge gap, then I'm very optimistic that we can get to these interesting states at very low entropy. Yeah, so I showed you how we can really start to address some really interesting regimes here now. And I would like to thank my students and postdocs. So these are the the people who worked on the quantum thermalization I first talked about. Here are the students and postdocs on the Fermionic quantum gas microscope. And I would really like to also thank all the sponsors of this research. And we have one third experiment on erbium that we're building up right now. And I would also like to thank all the former students and postdocs a lot. Thank you very much.
Thank you. So we have time for a few questions.
So back to the problem of this one-dimensional case.
Yeah.
I saw that you measure motion of holes, but I don't see how you measure the spin in this case.
We haven't measured the spin in that case yet. Immanuel Bloch has done one measurement where they, for a 1D system, they can actually measure spin up, spin down, and hole simultaneously. Like they can distinguish all. They can independently measure both spin states, which we cannot currently do, but we are about to be able to do. and then they're able to remove the holes and shove the spins together, like in the data analysis, and find that adding the holes just renormalizes your tunneling slightly and doesn't change anything else.
In the whole velocity you measure, then how quantitatively accurate can you do so that you know you really are looking at free hole motion, even in a spin background in this case, or you actually...
So in our data set, it's exactly, the slope that we get is exactly what we also get for a single particle. But we haven't looked into that with like super good precision. So one could do a precision measurement of that, for example, to compare putting a single atom or putting an anti-ferromagnet at various temperature in one hole. But we have...
About how much? 10% particle velocity you get?
I don't remember. So all of this data is really preliminary. We are actually taking more data now at colder temperatures.
Can you measure or demonstrate the quantum Zeno effect with a bunch of bosons in one cell and see if it's, decayed, suppressed?
So Zeno, one could. So we haven't really done this. Via imaging, you don't want to do it usually, because if you image, you also put atoms into higher bands essentially. Like, it's not just, so if I wanted to do experiments with Zeno effect, I would maybe use a different atomic species or different spin state of atoms to probe the presence of atoms, for example. And the Zeno effect, it does show up in different contexts here. For example, if we create a really strong loss somewhere, right, then that loss actually effectively creates a Zeno effect, and particles just never go there and things like that. Yeah. Mm-hmm.
Well, I wanted to ask this, I think is a dumb question, which is the optical lattice. I don't know the number. How much spin orbit coupling does it have?
So it doesn't have spin orbit coupling the way it's done now. You can engineer spin orbit coupling.
Parasitic. In other words, the spin isn't free if it's talking to the optical lattice. So spin-dependent interactions of the atom with the optical lattice.
With optical lattice. So in our case, it's actually, so we actually have, with lithium, the situation is such that we actually have great trouble to create any potential that does talk to the spin state. So it's very, very much common mode. There's really, like the spin coherence time, for example, is extremely long. It's very much not talking to the lattice. We would like to implement that, which is actually hard in lithium. With other species, that's easier, but it's very much not coupled.
So there's a follow-on question, which is, I didn't see an enormous number of numbers here, and you talked about 10 or 100 picokelvin.
So here, for lithium here, it's more tens of nanokelvin, yeah, but yeah.
It's 10 nanokelvin.
Yeah, I mean, as you know, the temperature scale matters as kind of in kb. The entropy is really what we care about,
But I don't know what, on these optical lattices, what is T? How many kelvins is T? You see, your temperature
little t.
relative to the
it depends, exactly.
tunneling.
Yeah.
And I didn't understand what that was.
I may not have given the, you mean the temperature in units of
how much it's tunneling.
of tunneling.
Energy, yes.
Right, yeah. It depends. It's some small fraction of T, yeah. So in different data was different values.
What you drew wasn't that. You showed this anti-ferromagnetic dome, and then you had this dotted line that was kind of just in it.
Yeah. Exactly. So this was roughly to scale. This was roughly to scale. Of course, there is no, strictly speaking, sharp transition in 2D. So in terms of, I can give you the entropy also. Oh no, sorry, I don't have it here.
The one you just passed.
Yeah, I think so. Yeah.
Yeah, there you go. Yeah. So what the cartoon that you
So this is roughly to scale here, right? This is roughly to scale. Of course, one has to be careful if you compare to cuprate, right? There are effects there with interlayer coupling that modify that a lot. But yeah.
There is an issue down there about whether it conducts electricity or conducts atoms in this case at all when it's cold. Now, if it's hot, everything's a conductor. So maybe that's the reason I was asking this question. So you say it.
I mean, yeah.
So the energy to tunnel an atom, and then you have the temperature. And the temperature over this tunneling energy, you say, is a small number. 10%, 0.1?
Yeah. Right. I mean, we are like currently a factor of few what is believed where the...
You're talking to all these theorists who think they know so much. Did they say it's an insulator there? Did they say the charge should move? Or do they say it should not move?
I mean, one thing that's nice is, you mean in the mud insulator?
Yeah. Yeah. In the fermionic one.
In 2D, yeah. No.
See, because there's this phenomenology you have in the solids, which of course, relatively speaking, you get much colder, that you dope them a little bit and the charges won't move. They're stuck. And it's been an argument for a long time about why that is. So, anyway,
right.
I think what I've learned.
I mean, we could do this. So these kind of things would actually be for us kind of the easiest next things to study, right? Like as I showed you.
Temperature, right? How cold can you?
Yeah. Right.
In this thing, when you've got all these spin degrees of freedom, I mean that's hard, right?
Yeah.
You have to use this trick with the gas outside.
Yeah. Right, but so we're just starting to explore that, and that seems to work very nicely, and we can do we're planning to do advanced versions of that where we can, like, so far we can extract as much entropy as we would expect, actually. So that, in that sense, it works very nicely. And in the extreme case, we make a band insulator. That's actually interesting that in the band insulator, we get very good fidelity over our coherence time, which is very promising that, that you can really, create, I mean, we have like 15 by 15 lattice sites with exactly one spin up, one spin down atom, like as a quantum register or as a starting point. That is a fantastic low entropy state. But even the fact that we were able to make that was a bit surprising to me, because I thought, there's Pauli blocking, and how do the holes from the middle of the band insulator even go outside? But what we showed experimentally is that we can do that, and that we can really get an extremely good band insulator. So that's one of the examples where we can show that, yes, just the fact that we can create it shows that the holes can move out and we can create that band insulator.
I was just wondering why the measurement readout beam collapses the wave functions, but your potential beam and your lattice beam don't.
Yeah, that's a good question. So the difference is the following. Our optical lattices, we are very far detuned with the light. Right. So the resonances are quite narrow. They are a few megahertz wide. And then the optical lattice beams is many terahertz detuned, right? It's like 1064 nanometer light where the transition is actually red, right? So there's really pretty much no photon scattering over the time of the experiment. Whereas the beam for imaging, that's exactly on resonance or close to resonance. And so then if you shine light on there, you scatter photons quickly. And the first photons that you scatter are kind of collapsing your wave function. Right? But yeah, right, if the lattice lasers would scatter, then they would also collapse the wave function, so you don't want that. And that's actually a heating mechanism of optical lattices, but luckily that's not limiting for us so far.
So when you say you take a snapshot in time and you turn off all the tunnelings, is that done so fast that there are no dynamics involved and all the other processes are much slower?
Exactly. So we can do that. We can do it this far. We can actually also play tricks if you want to squeeze out the coherent excitations in the mud insulator, and then we can ramp up not super fast but slightly slower. So you can do a lot of additional things. But yes, Our control is faster than the time scale. So we can be arbitrarily fast.
I would like to ask one question about the Manybody localization
Yeah.
data you showed before. So can you say a little bit more about what the measurement is that actually distinguishes Manybody from the single particle case?
Yes.
And also what,
It's looking at configurations, essentially. So if I just measure the particle number in each of the site after the non-equilibrium dynamics, it turns out that this shows up as a correlation in configurations, like in the left half. Is there a correlation between a certain pattern appearing here and here? And that correlator starts out at 0 and then builds up goes logarithmically. And in numerics, we found that it exactly scales like the configurational entanglement entropy. Because, and the reason is, it's kind of it is a typical measure of correlations, right? And and everything is chaotic anyway, so it doesn't matter which correlations you measure. If you measure typical correlations, then you measure the right thing, right? But that's really kind of, to many theorists we talked, this was a new idea that you can split it up into this particle entropy, configurational entropy, and that seems to make a lot of sense and really gives us a handle now to measure like a positive quantity, you know, like something that is really like the quantity that grows. What makes MBL special? The part that is given by the many-bodiness, like by the many-body interaction, and the part that then grows logarithmically in time.
Okay, so I think we probably
Yeah.
that should
Oh, sorry.
call it a day.